Welcome back. In this session, we'll start with the discussion on digital filters. Let's start. Now, there are two types of digital filters. These are referred as FIR, means finite impulse response filters, are in short FIR, and infinite impulse response filters, in short IIR filters. So, as the name suggests, the terminology comes from actually the duration of the impulse response. You can say here the duration of the impulse response is finite. Here the duration of the impulse response is infinite, very simple. So based on what is the duration of the impulse response of the system, we can classify that system either as FIR or IIR filters, right? All right, so there are two classes of digital filters or digital systems. One are referred as IR systems or IR filters. Another is referred as FIR filters. Now let's first see the distinction between the two. Let's see the distinction between these two type of filters. All right. So let's do that. Let's first learn how do we distinguish between these two type of filters. All right. Now what's the difference between these two type of system and filters? All right. So let's say this side we have FIR system or FIR filter, and on this side we'll write that's an IR filter. Now, as the name suggests, here the impulse response, or we can say the impulse response is finite. Is finite, and the duration of the impulse response is finite. Here, the duration of the impulse response is infinite. Impulse response duration is infinite, right? So examples for this. Now example of this is h of n is the impulse response of this finite impulse response filter is, for example, let me give a very simple example, 1 comma 1. So this is a finite impulse response and the duration is from 0 to 1, right? Or you can say h of n is, let me take, let's suppose 2 raised power minus n u of n, where when n is from 0 to 4 and it's equal to 0 otherwise. So what is the duration of this impulse response? From 0 to 4. And we can also write it as a sequence. We already know this. So the values will be, when n is equal to 0, this will be 1. When n is equal to 1, this will be 1 by 2. When n is equal to 2, this will be 1 by 4, right? So when n is equal to 3, this will be 1 by 8. When n is equal to 4, this will be 1 by 16. So this is our impulse response of the system. Same way, the example of this with an impulse response, we can say is 1 comma 2, 1 comma 2, 1 comma 2, and so on, right? Since this has an infinite duration, we say this is an infinite impulse response system. All right. Or one more example of this is a raised power m u of n, this is minus m for all, right? So this is defined for all n. So the duration of this filter is infinite, right? So I hope you have got the idea what doing in the finite and infinite impulse response. So I hope you understood the example. I hope this is very clear now. Next, this is the first difference between these two. So the duration, in terms of duration, the duration is finite and infinite, right? I hope you have got the idea. I hope you got the idea now. Right? Alright, now the second distinction between these two systems is finite and infinite impulse response filters or systems. Every filter is a system in discrete time. So we can say the second difference between the two is the difference equation that models the FIR and IIR filter. Now the general, let me draw the general difference equation of an FIR system of order m. Let me suppose this is of order m is ak x of n minus k, where y of m is the output of this system or this filter and x of m is the in. So this is the second step. So this is characterized by this difference equation, means there are no previous outputs in this. So there are no previous outputs. You can check there are no previous output terms. In other words, there is no recursion terms. Right? In FIR system, there is no recursion. Right? So there are no output terms involved in the difference equation. Right? This is the difference equation that describes an FIR system. Now, same way, an IIR system is described by this difference equation. A running from 1 to m, a k y of m minus k is equal to summation k running from 1 to m x of, sorry, let me, x of b, b x b, bk x of n minus k. So now you can see the the present output is y of m is dependent upon the present and past values of the input and the previous values of the output. You can check it is also dependent on previous values of the output. Right? So there is recursion here. So we have recursion here. Right? So there is recursion here. There are recursive terms. These are referred as recursive terms. And the feedback terms. These are also referred as feedback terms. In signal system theory, these are referred as feedback terms. There is no feedback here. You can see there is no feedback. Right? So there is no feedback. Alright. So this is based on the difference equation which models the two systems. Here the system is discovered by the nth order difference equation. Here the system is discovered by the nth order difference equation. Right? So that's why this sometimes is written as like moving averaging system. Moving averaging system. This is referred as ARMA system. So FIR systems are actually ARMA system here. I think the previous class we saw what the ARMA and the moving average here, right? So this is one more distinction between the two. Now the next distinction between the two is between FIR and IIR based on the transfer function. Now the transfer function can be obtained from the difference equation area, right? Taking the z transform of this, we obtain the transfer function of this. So say taking the z transform of this on both sides, this will be k from 1 to m a k. Let me not use ak here. Let me not use ak so because there is bk output here. Let me keep it consistent and let me keep the order equal to m so that it becomes consistent with that expression. So this is 1 bk and this is 0. It starts from 0. That's the first term here. 0 x of m minus k. Sorry, we'll write that z transform of that expression, so it will be summation k running from 0 to m bk 0 is to minus k x of z. How do you obtain the transfer function? Output by input. So output by input is h of z is the transfer function of the system. So the transfer function is, this is the transfer function, right? As you can have a look, there are only zeros in this. There are no poles. So there are no poles in FIR system. So there are no poles in FIR system, right? Now an IIR system is described by this difference equation, right? Now this difference equation, so we can write the Z transform of this, taking Z transform on both sides, we write Y of Z is summation K running from 1 to M, AK 0 is from minus K, Y of Z is equal to summation K running from 1 to M, dk 0 is from minus K, x of Z. Now taking this common and dividing it by x of Z, we'll have the transfer function of this system, which is given by this. We have derived it so many times. 1 plus summation K running from AK 0 from minus, right? So this is the transfer function of this system, right? So there are both poles as well as zeros. You can check it. So there are both poles and zeros in IIR system, right? So this is the another distinction. Now next distinction is the fourth. As there are zeros only, you can see there is no denominator term in this. Where there are zeros only, so you can see there is no denominator, right? So that means no poles. That in other words means it is inherently stable. Stable system. So FIR systems are stable systems. So FIR systems are stable systems, right? Because there are no poles. There are no poles. That means if we see the Z transform approach, there will be the system transfer function will never blow up, right? Now the same thing for this, as there are poles and zeros, so that means it may be unstable. So this may be unstable. May be unstable. Now when will it be unstable? If the location of the poles is outside the unit circle. Pole is outside the unit circle on Z plane, then it may be unstable. So this is the advantage of this, is the biggest advantage of one of the biggest advantages of our fire system. As there are no poles, that means these are inherently stable, as there are no poles, right? So this is one more distinction between these two. So this is a fourth. Now, now if you remember Z transform, please revise that. You know if the pole lies outside the unit circle, then you know the system will be unstable. Z transform. Please revise that. Right. Now the next distinction between these is based on this linear phase. So the next distinction you can say, we have linear phases possible in this, and this is very important for applications like music, like audio, like speech, or in short the communication applications. This is very common. You can have linear phase in a file system. How we can have linear phase? Now let me show you how we can obtain linear phase. We know Hz as the Z transform of a fire system. We obtain it is equal to 0 to M dk 0 is power minus k. Now how do I obtain the discrete time Fourier transform of this? you remember, just put z equal to e raised power j omega. So that will give us h of omega. Put z equal to e raised power minus j omega. Sorry, j omega. Is equal to e raised power j omega. This will give this. Now you can see the phase here. The phase here is embedded here, and the phase you can see at omega is minus omega t. Depending upon the number of terms that will manifest, and you can see it is linear. It's a linear function of frequency, so it's linearly varying with respect to linear versus omega. So the phase is linear. So this is true. This is true in this. But if you see FIR systems, we know the transfer function is hz is equal to summation bk is equal to minus k n1 plus summation over k1 to n ak is equal to minus k. This is k and from 0 to m, and we can obtain the discrete time Fourier transform of this. Discrete time of Fourier transform of this will be x of omega, which is obtained by substituting z equal to e raised power j. So the phase you can see you have to add the phase of this and the phase of this, and you can see it will be a non-linear function of omega. You can see phi of omega will be non-linear. And what will happen if it is non-linear? This will simply introduce distortion in the input signal. When you pass a signal through an IR system, the output signal will be distorted, right? Now, so this is the advantage of FIR system is what? IR system. This is very, very important. Now the another advantage, other advantage of IR systems or FIR systems now is this. This is very, very important. Now the advantage is, remember the advantage is that to realize an IR system with some frequency characteristics, means to have a desired frequency response, you require less number of terms in IR system. To get a desired frequency response in IR system, less number of terms is required in IR system, right? Means what do we mean by less number of terms? Means less hardware. Less hardware. This is the advantage of IR systems or FIR. So more number of terms will be used in FIR systems to get the same desired response that you obtained in with IR systems. So more number of terms will be used in this. So in other words, more hardware. We saw the realization of these systems in the last class, if you remember. We have already done the realization part. The next that's the realization. We have already done that. And in this we learned one, that's the tap delay form. If you remember that. Tap delay form realization. And in this we learned two ways. One was the direct form 1, and second was the direct form second. Right? Direct form second. So these are the several distinctions between FIR and IR system. There are others, but let me give you one. So in short, IIR and FIR based on this distinction is based on the impulse response duration. So if it is finite duration, then we call it FIR. If it is infinite duration, we call it IIR. Right? Now the other distinction is between these two are like this. So please revise these. In the next session, we will see some simple examples of FIR systems or FIR filters. All right? Let me end this with here.